So these patients visit the clinic every 6 months. And every 6 months, the doctors look at these patients, look at their status, and based on their status, they prescribe medications. So we have a patient here, a patient at any given time t. This is, the study started in 1993, and it's still ongoing. And we have data until, just in this data set that we are looking at, we have data until 2018. So we got a sequence of visits made by these patients, and there's a sequence of actions taken by the doctor, which is prescribing medications. And then they're measuring, among other things, the viral load. And so reduction in the viral load can be construed as a reward. So you have a triplet, S, excuse me, S, A, and R. S is known as, is the set of variable features. That's the state variable. The state variable is nothing but a t-dimensional vector, x1, x2, xt. And like I said, this is a combination of their demographics and their labs and all the other things that are related to the human at any given time t. So this is all indexed by time. Remember that these patients visit every 6 months to the clinic. And then during that time, this t keeps changing. Okay, you've got xt. And also I have to index this by time also. But you understand that problem here. If I'm to avoid clutter, I want to write x1, x2, xg, index by t. And now you've got this A here, which is an action set, which is a set of actions that the doctor can take. This is a set of K elements. So this could be the different types of medications that the doctor prescribes. And then there is a reward, which you are measuring the viral load. So it could be the viral load, it could be hemoglobin, it could be the blood, urine, and nitrogen, it could be creatinine, it can be the WBCs, it could be the RBCs. All those things can be measurable as well. So we will see an example here where we are looking at the combination of the viral load and the other variables. So this is so as you can see, you have time here, and over time patients are visiting these clinics, and we have a time varying state variable which is describing the patient, and in the language of RL, this is the environment. I have all these slides, but I still prefer to write on the board. So you got the environment, and then you got the, so how does this work? So you got an environment here. And then you got an agent here. The environment provides a state information to the agent. This is a picture you probably have seen 2,000 times. And then this loops back, and then it picks up an action from this action set A, and this I will denote by script A here. And so what happens is that the environment also sends a scalar variable R, which is the reward, and this cycle repeats. So this is how this reinforcement learning works. So if you understood this part, and you understood a little bit of probability, then you're done. Everything else is decorations and job security. This is as simple as that. All you need to know is just some contribution of probabilities and marginal probabilities, which even I know. So it's that simple. It can, in an application, it could be very hard. This could be a large dimensional vector. And then there is this issue of exploitation versus exploration. Exploitation is, do you want immediate reward, or are you looking for immediate reward, or are you looking for long-term reward over a longer period of time? So those are all the issues that come into picture. And there was someone I was talking to just a few minutes ago, just before this meeting started, and then they were saying that they were applying it for some scheduling problem, but it turned out to be very, very hard. But in the world that I live, in this HIV environment, it might be, I don't have it, the results that we get are not that doctors can use, but all this demonstrates is how RL can work in dealing with medical problems. That's the goal here. Okay. So I'll give you a little bit more information about this whole thing, about this data that we are seeing with the data that we got from NIH. It is called WIHS data, Women's Interagency HIV Study. This was commissioned by NIH, as I said, and it's been ongoing for a lot of time, a number of years. So that's the data that we have right now. Our study here. So the idea here is that this data is all observational. People are coming in, we are getting some measurements from them, and then we are trying to compare the efficacies of drugs. In a standard problem, what would happen if it's a randomized clinical trial? What happens in a randomized control trial or a clinical trial? What happens is that there are volunteers. Volunteers are recruited for a study, and then these volunteers are divided into two groups, right? Treatment and control, or placebo. One set of the treatment people get the experimental therapy, and the others get placebo, a sugar pill or something like that. And so what happens here is that because of the randomization, all the baseline features are the same for both variables. If there are any unmeasured weight features, what we call unmeasured confounders, they are the same for both groups. And therefore, we are looking at equivalent set of populations here, and then the comparisons are valid. But that is a controlled randomized clinical trial. I, as an experimenter, as the designer of the study, have the ability to recruit patients and then randomize them into two groups. But in this data that we have, that's really electronic medical data, EMR and EHR data. You all have heard about it, right? So EHR and EMR. So there is no randomization here. You get two groups of people, and then you have to compare them. So the question is that you can compare them, and FDA said that you could compare them, but you have to show the equivalence between those two populations. And that's a painful problem, right? I mean, imagine you have thousands of features, right? So I'll keep in our language we call them covariates. I'm more comfortable using that word covariates than features, excuse me for that. So we have high-dimensional covariates, which is equal next to XD, and then we are trying to compare equivalence between them. We are looking at the high-dimensional data, and we are looking at the probability distributions of this joint probability distributions of these two sets of features or covariates, and that's a difficult problem. And so that's one issue with observational data, and that's one stream of research. How do you show equivalence between two populations when your data is high-dimensional? People use standard techniques such as principal components, etc., but FDA will not agree for some synthetic variables being shown to be equal. The syntheticness of, if that is a word at all, of these principal components or linear projections is nothing but linear combination of the basic set of covariates. And that's, sometimes it has meaning, sometimes, and most of the time they do not. What I mean by that is that you have a vector x, and that vector x is multiplied by a vector w, and that gives you another vector z. And this z is just a linear combination of, this is x1, x2, xd times w1, w2, wd, and that summation is summation xi d wi, I equal to 1 to d. So this is your new vector z. And summation xi times wi, based on those covariates, is really meaningless. So those comparisons are not valid. So that's another one set of ongoing research that's going on right now. You can do it in terms of looking at probability distributions of these features here. And then you can compare through standard techniques. One of the techniques that we know, that we teach in our undergraduate, yeah. Was there a question there? Oh, sorry. Oh, okay. Is that do a Kolmogorov-Karnoff Smirnov test or something like that. How many of you have that? How many of your statisticians here? Mathematicians here? Okay, 1, 2. Computer scientists here, everyone probably. Algorithms. Okay. So most of my talk is going to be about linear algebra, and it's going to be about probability theory. And then I'll talk about HIV, and then reinforcement learning is nothing but the combination of all these two, of the first two, and HIV is an application. So please do stop me to ask questions. If you don't ask questions, I'll ask you questions. That's fair, right? Okay. Now, what we'll do, the other part is that when you have a clinical trial and you have a promising experimental drug, and then you do randomization, that is somewhat unethical, because here I am very sick, and then there is this promising drug, and there's a non-zero probability that I am assigned to the placebo, and I get a sugar pill, and I have to drive 10 miles every day or every 1 week to get this sugar pill, and that's unethical. And so what we do, and in economic studies also, you know, if you're trying to find out which system of education is better, public school or private school, it's not fair to send me to public school and him to private school. I mean, I'm not picking on you. So that's unfair. So what people do, what FDA says now, is that in medical studies, anybody who volunteers for this drug gets the drug. Everyone who volunteers gets the drug. There's no randomization. They said, however, that you can find an equivalent set of folks from electronic medical records and electronic health records. And they are undergoing treatment through the state-of-the-art medication, not the experimental one, the one that's approved by the FDA. And that's called standard of care. So now again, you have that issue of, you have data where people have volunteered, they all get the experimental drug, and the second arm, which is the placebo or the control trial, it could be control arm, it is receiving, that data is scraped from EMR. The first the type of data where we are getting data from physical patients, excuse me. That is the data from controlled experiments, treatment. The other one, that type of data is controlled data. The second one that is scraped from EMR and EHR is called observation. So you got two types of data here that we are dealing with: observational data and control data. So that's one. So You got observed, and now in the HIV problem that I'm talking about, the two arms are both observational. In the sense that you got an antecedent drug that's already in the market, that's being used for women, and then when we're collecting all the data from them, that's available in EHR and EMR. And then we have the new drug that's being prescribed to patients by these doctors as an off-label expansion, under off-label expansion. And the two arms are both observational, and you have to study those problems. So, how do we overcome this problem? Machine learning is coming to help here. In that, reinforcement learning is an example. So this EMR, EHR data that I keep belaboring about is called RWD, real world data. And then there is this other data, and using that data to find signals in that data is called real world evidence. So it's real world data for real world evidence. Okay, so this is redundant right now. And again, something that I have to tell you whenever I talk about these things, the correlation between what I say and what you see on the slide, the correlation is almost zero. So do not map what you see on the screen to what I am saying. So how does HIV work? HIV works very similar to how COVID works. It's an RNA strand, it's a single strand RNA that binds to the cell here. I can't even find my, that binds to the cell here. And then once it binds to the cell, what it tries to do is that it tries to, and it has a protein called reverse transcriptase, RT. And that reverse transcriptase enzyme or protein tries to penetrate the cell membrane, and then it converts itself into a DNA and takes out, it replicates itself within the body, and then it spreads all through the body. That's how HIV works. Even COVID works exactly the same way. A single RNA strand, it needs a host DNA, it penetrates the body, the cell membrane, and then it takes over the function, normal function of the DNA, and then it replicates, and then it goes and affects our lungs in the case of COVID, and it kills us. That's what it does. So how do we deal with this problem? There are 3 or 4 different types of drugs that people talk about. These are called NRTI, NNRTI, PI, and II, and combinations of them. So the NRTI, it's called nucleoside reverse transcriptase inhibitors. And look at that set of drugs that we got there. So PIs and NRTIs and PIs and IIs, etc. So this NRTI, what happens is that when this RNA strand of HIV or COVID tries to penetrate our body, it has to bind to a site on the cell membrane. When it tries to bind to a cell membrane, this guy will go and block that area where there are only some parts of the cell membrane at which points that the HIV virus can attach to the cell. So this NRTI blocks that. So that's one way. And NRTI, I heard, is that it tries to confuse the HIV virus. It says that this is not where you should bind, and it will send it to a hostile place, an environment which is hostile for binding. So that's NRTI, NNRTI. So there are NRTI, NNRTI. PI is also a type of a blocker, and that is usually used when the HIV, the patient has been at a very high risk for HIV and is borderline HIV patient. So people use, doctors prescribe not just these three or four drugs, but cocktails of them. So that creates a lot of combinations here. So that's typically how the, yes?
Sorry, I was actually curious about that, like your actions at actually having enough variation, because I don't know anything about the medical field, but it seems like I would think doctors would basically pick whatever was the best available treatment and just do that. But you're saying that's not what they do. They try a bunch of different things.
So it's not a bunch of different things that they try. It's the number of the drugs that they have, the cocktail of drugs together, they help the prevention of HIV. It's not that they're trying just a random collection of drugs.
Right. I guess that's my point. Like in the historical data, when you have a bunch of doctors trying the same things at the same time.
So yeah, I mean, we do not see that kind of a variation because there is a patient-to-patient variation here, and we do not see that much of a. Actually, you would see that in a preponderance of cases, what happens is people they use NRTI drugs, but in the prescription of the drug, there might not be that much variation because there's only a few combinations of drugs, but there's a lot of variation in the covariates that's related to the patient, the state variable. That's what we see. Does it answer your question?
Yeah.
Okay. Yeah.
This study appears to have lasted over 30 years. So over that period of time, some new drugs must have come online.
Yes.
And some drugs might have been superseded by new drugs that came online.
Yeah.
And also some state variables might have been measurable that weren't measurable in the past.
Right.
So I imagine that whatever RL behavior you're attempting to modify is going to be based on different classes of state variables in the state 1998.
Yeah. Yeah. Right. So that is a very fair point. So what we do is that since we do not know about people dying and then the length of the study length is over 25 years to 30 years, etc. But we still want as much data to just do our analysis. Instead of rejecting them, what we do is we do clustering based on this large number of covariates. And within those covariates, clusters of patients with those covariates, we do the analysis here. That's what we try to do. So as far as oral drugs are concerned, the thing has been that, as you can see, there are quite a few different types of drugs here. Yeah, here. You can see different types of drugs here. And some of them are old, some of them are new, but the fundamental chemistry of all these drugs are approximately the same. And that's why I was advised that it was still okay to compare drugs from 25 years ago to the present. That's what I've been told.
Do your patient clusters change over that period of time?
Yeah, we do see patient clusters. We do see different clusters forming within this 30-year set. That's what the clustering is based on the state variables, the environment of these patients. Within that set, we have similarities. And then the question is if it is a patient who is from 1993, who started treatment in 1983 versus a patient who started in 2016. In terms of, there is some similarities that we have seen, and the reason that we see those similarities simply because the measurement of this HIV, this viral load, and we are looking at this blood, urine, and nitrogen, creatinine. Those are the levels that they're looking at. In terms of them, they're similar. And so that's what we do. But in terms of age, there are patients, a patient who is at high risk for HIV in 2015 doesn't necessarily mean that the patient is younger than the patient who is at 1993. So there is that's why we get these clusters, and within the clusters, we try to do the analysis, and whether it is appropriate or not, to the extent that we talk to the medical people, they're saying that it is reasonable. I mean, they don't say it's reasonable, but that's what it is. So, does that answer your question? Okay.
I can make a comment with in the data that you collect, you have the information from like when they first got HIV. So for example, someone who first shows up in 2016, did they get HIV around 2016 or did they get it in like 95?
So the thing is that what we know is that the first time that they have come to the clinic, the first time that they have registered for the study here, that's all that we know.
Okay. So you might be comparing people who, there could be like a survivor bias where like people who you're getting in 2016 are people who have like survived HIV for 20 years, as opposed to people who just got it like last year.
Yeah, there are patients like that. There are patients, so remember, these are not HIV patients. These are patients who are at very high risk of HIV.
Oh, okay.
Yeah, that's what it is.
I see.
Okay. So again, I'm not a doctor. Well, I'm a doctor of the philosophical kind, not the medical kind. So if I didn't answer your questions, I'm sorry. Okay, so back to reinforcement learning here. What does this do? Like I said, it has a state variable. You have an action set, and you have a reward set. You also have what is known as a policy. Policy is what action do you take. That could be a stochastic policy. The stochastic policy is usually defined by pi of a given S. This policy is nothing but you have the actions, the state space, and you have the action set. And it's a mapping from the state set, the set of variables in this state, and the action here to a reward. So this is nothing but the probability of an action that you take, A equal to, A belongs to A, given a state, S equal to S. Again, I'm indexing this by T here. So that's the policy here. Like it says, that a policy is a mapping from the perceived states of the environment to the actions to be taken in those states. So that's what the policy is. Then you have a reward signal that defines the goal. And each time step, the environment sends a single number called the reward to the reinforcement learning algorithm. The objective of the algorithm is to maximize the total reward. That is what we're trying to do. So the reward signal really indicates what is the best reward in the short term. Also, it indicates what's good in the long term. So the value of a state, you can define the value of the state. What is the value of the state? That's what we want to define. The value of the state is the expected value of the reward given the state is equal to S. That's we all know what an expected value is, correct? The expected value is nothing but an average. The expected value of a random variable here is nothing but, in the case of a continuous random variable, is x times f of x dx. And in the case of a discrete random variable, its probability of x is equal to times little x. So that's what we're trying to compute here. That's the value of the state. And so this is, if you look at this reward here, reward, you start at a state S, and then you have a reward you see at time t plus 1. And then what we see is that we also are looking at the long-term rewards. In a long-term reward, what happens is that you got some scalar value gamma times rt plus 2 plus gamma squared times rt plus 3, and it goes, etc. And this given state st, given that you start in, this vertical symbol here means that you start in, given that you're starting at state st equal to x, what is the long-term reward here? The gamma here is chosen between 0 and 1, which means that in the future, you're not certain about the future. So and when you choose a value of gamma between 0 and 1, what happens is that this is exponentially decreasing. So in the future, the reward, the weight that you give to a reward is very small. So ultimately, you can also define the value of the state. In the long-term value of the state is given by the expected value of g of t, given your starting state st equal to s. Okay? So the expected value of gt, you can write it as expectation of rt plus 1 plus gamma times rt plus 2 plus gamma squared times rt plus 3, etc. so on, given st equal to s. So which I can, if I take the expectation inside, expectation is a linear operator. It's rt plus 1, that given st equal to s, plus if you look at this guy here, we can write this guy as gamma times rt plus 2 plus gamma times rt plus 3, etc., given st equal to s, which I can write it as expectation of rt plus 1 given st equal to s plus gamma times this, you can write it as, see this guy is very similar to this guy, I can write it as v of s at t plus 1 given st equal to s. So that's a long-term expected value. Are you appreciating this, or I'm just killing you with all these symbols? Yeah.
I just had a clarifying question on the reward. The reward signal is the viral load, right?
Yeah, in this case, it could be viral load, it could be a vector also, it could be a combination of viral load, hemoglobin, and
You want to generally maximize rewards, so you just flip the sign.
yeah, to maximize the reward, yeah, the viral load should be small. Yeah, yeah. Any other questions?
Yeah. Precisely the reward function. So, have you experimented with other kind of reward functions, or for instance, here assuming that the viral load of, you can transfer to the present the viral load of the future. So this kind of assumptions, have you worked in this direction of revising these assumptions, or you just have to stick to them?
So we have started in this experiments here that we have done. It's the standard implementation of reinforcement learning. All that we have done to understand the uncertainty in the future rewards is playing with the gamma, the scalar gamma. that's chosen between 0 and 1. Other than that, we have not done anything. Okay, so the reason that I wanted to show you this is not because it's fun, it's just that we want to understand. We are computing the average, this guy G of t is given by this summation, this guy here. It is a long-term reward here, and we are looking at the average reward over a long time. The average reward of a long time, we are breaking it up into 2 pieces, which is that the average immediate reward, the expected reward at this time t plus 1. Because at time t, I'm in state S, and now I'm taking an action. And so I observe my reward at time t plus 1. And that's what I'm seeing here. Plus gamma times the value of the state at time t plus 1, given that I started at state S. The reason this is all simple, the expectation, like I said, is nothing but a probability. And that's why we are saying this. So we are trying to bring in this idea, this notion of uncertainty. Yeah, in one way is to deal with gamma, and also to compute the probability of S equal to the conditional probability there. So, yeah.
Yeah, I have a question. Like, so your output is a policy for deciding what to do?
Yes, the output is what is the best policy in terms of treatments for any given patient.
And my confusion is just offline versus online learning. You guys are just learning one optimal policy, but you don't look at the, do you look at the history of this patient?
So see, okay, in terms of history, what we are looking at is that the patient visits the clinic every 6 months. That's the data that we are looking at. It's a sequential decision problem. It's a Markov decision problem.
So the state is the entire history.
The state at time t. The state of a patient is the patient demographics and labs at any given visit time. So you got the state variable changing at every visit. So my age changes, my hemoglobin changes, my behavior changes, etc. All that state variable is changing. That's why when I wrote this graph at the very beginning, actually it's right there. See that the agent is the real world, that's the environment at the very top. And then that sensory information is the state information that is being sent to the agent. And the agent takes an action and then transforms it to the environment, which is the state variable. That is what is happening. So the important thing to understand here is that this guy here is time varying. That's my state right now. Today when I go to the clinic, I got a set of covariates x1 through xd, which is my demographics and my labs. That's what this is. So then it provides it takes an action here, and then the action information is, so that means that now I have received a drug. The doctor, at this time, I have gone to the patient, the doctor gave me, he decided to give me a medication, that's the action I took, and then that information is propagated back. And that information being propagated back simply means that the effect of the drug that took on the patient, and so the state of the patient changes, and then the reward signal is sent to the agent. That's the data here, sorry. Yes, sir?
Yeah, I had a question on the reward as pertains to those covariates. So you mentioned labs. So with HIV, I know CD4 count is probably the most...
Yeah, CD4 count. Yeah, I was going to talk about the CD4 counts and CD8 counts. So we look at the ratio of CD4 counts and CD8 counts. If CD4 over CD8 is greater than 1, then we say that the patient is safe. If CD4 over CD8 is less than 1, the patient is at risk. Yeah.
So is that the sole metric for the reward function, or are there...
Well, okay, like I said, and as I answered to him, it's not just the reward, that's just the CD4 and CD8. We also look at the hemoglobin, and WBC. So let me show you.
What does
how-
CD4 and CD8 mean?
Okay, I'll explain to you the CD4 and CD8. The CD4 is that, okay, here I am, talking to you nicely, minding my business, okay, and then I'm affected by a virus. And so I have an immune system. The immune system is looking for foreign invaders. So its job is being a policeman. So it's being a sentinel. It's looking for foreign invaders. That's called a T cell. So then once it detects that there is a foreign invader in my body, what it does is it goes and tells another cell called the CD8, and the CD8 launches an attack. So the CD8 is fighting with the virus, and then sometimes they win, then in which case we are fine, sometimes we lose, in which case we probably die. So that's the CD4 and CD8 cells in our immune system. And what we look at, like he said, like the gentleman said, is we look at that ratio CD4 over CD8. That's one of our proxies for this, how the immune system is working. And in addition to that, what happens is that you got this hemoglobin and this WBCs. So how does that work? The red blood corpuscles that the heart pumps into the lungs, it does not have any oxygen in it. We are breathing the oxygen from the atmosphere, and then this hemoglobin is the one that helps to oxygenate the RBCs, and those are the red blood cells that are keeping us alive as we speak right now. That's the physiology of how our body works, our immune system works. So going back to your question, so if our hemoglobin levels are compromised and our WBCs are compromised, our bone marrow has WBCs and they have to convert to RBCs. If the WBCs are low and then the hemoglobin is low, then we got a problem. So our immune system is compromised, and so we are susceptible for other diseases. So it was another hand that went up. Yeah.
So you mentioned that the patients are coming in every 6 months, right?
Yeah.
So the drug which is given to the patients and then the measurements of all of these things are done at the same time. The question being, like, if let's say a new treatment or a new drug is given to the patient, there might be a lag before their viral load and other things start to go down. So the reward which you create, is it after a certain interval, or does that not matter because it's longitudinal?
So it's longitudinal data we are not looking.
Eventually you'll capture.
Yeah, we will capture, but that's what we do. Yes, sir, you were asking.
Yes, I have a question. I assume that to compute the expected value for t plus 1, or t plus 1 at time t, you're going to need a probability distribution of what that t plus 1 is going to look like.
Okay, so
Is it computed on a policy basis, or is it computed on a per cluster?
it's within a cluster, you're looking at the problem. What is happening here? If you write the picture here, so you start at time t. This is my time interval. You started as 0, you got some stage 0. Then you go to S1, you go to S2, and you go to SS. That's the number of states that we have. That's the cardinality of these whole states. So from here, that's one thing. The other thing that you can do is that the starting state is 0. Then you can take action A1, then you can take action, this is state S1. You can take action A2, blah, blah, blah. Let me write it this way, action AK. That's what you got, okay? So you got, then you can also go to state S2, And that also has the same thing. A1, A2, blah, blah, blah. A1, A2, AK. So that is what we have. Given that this is the diagram that we have to compute, like you asked, what is the value of a state. Let's compute the value of the state under this policy that you're talking about. The policy is the actions that I take, correct? So now let's compute this. The policy, we define it as pi of AS. So under that policy here, pi, you're looking at the overall, the expected value of G of t given ST equal to S. Now, GT is nothing but the reward, right? If GT is the reward, so the expected value is nothing but the reward, the summation over all R, or over all the rewards that you have. That means times R times the probability of R given ST equal to S. Correct? Now you have the probability. What's the probability of R given ST equal to S? This then turns out to be R times, added over all values of R. Now I have to go through different states. I go from S0 to S1, S0 to S2, etc. So now I have to worry about adding over all. I'll write this S1, S2, SS. I will write it as S prime. That's the t plus 1 state. Now you will write probability of R, S prime, given ST is equal to S. Yes, now I'll finish this question and then I will
I
add.
want to ask that, because you have patients who are specific states, you won't know whether a patient actually went from S0 to S2, right? Because like, one patient will only follow one particular path and the other patient is following a totally different state.
Yeah, yes, of course you have those issues. I mean, one patient will go from state S1 to state S2. Your S2, S1, and my S2 are not the same. Okay, so Rakshak, I request that we stay here till 10 o'clock. Okay, so the thing is that patients, there is what is known as propensity scoring. You might have heard, how many of you have heard of propensity scoring? In propensity scoring, what happens? Propensity scoring says that you have a baseline set of covariates, and now what is the probability what is the probability of treatment assignment given my baseline covariates? Treatment assignment is what? I mean, you're assigned to group A or group B. If you're only comparing two groups here, let's say NRTI and NNRTI, you get probability of T equal to NNRTI given the baseline covariates. And how do you evaluate that probability? My mother told me that just use logistic regression, right? Probability of T equal to 1 or T equal to 0 given the baseline set of covariates, which means that you're computing probability of T equal to 1 is nothing but some X transpose times beta, correct? That's standard regression that we do. Actually, this is, I lied to you. This is log of 1 minus T equal to 1, which means that probability of T equal to 1 is nothing but e raised to the power of beta naught plus X transpose beta divided by 1 plus e raised to the power of beta naught plus X transpose beta. And we all have seen that in our careers as statisticians and data scientists. Right? What is that? That's our softmax function that we learned when we were this high. Right? So, why am I writing all this? So, the propensity score, to go back to your question, the propensity score, the way it works is that you have a state variable, and that state variable is d-dimensional. And I took that d-dimensional variable and I have cleverly converted into a probability of t equal to 1 based on those covariates. And so I have only one number. I reduced it to a scalar. And so suppose I have a set of covariates for which I compute my probability of t equal to 1. And I compute your probability of t equal to 1. And if I am within an epsilon, and you choose that epsilon. And if we are within that epsilon, then we are matched. So that's the approach. Okay, back to your question, sir. Sorry to distract myself. So this is the probability that we are computing. Now, what I did not do is that I completely ignored these guys here, the actions, the policy. That was the question that you're asking. That is given by R times. I will add over all S prime and A prime, probability of R, A prime and S prime, given ST equal to S, which I can write it as summation over R, all R times. I can write this as summation S prime, A prime, probability of R, S prime, given A prime, ST equal to S. See what's happening. So here what happens is that I can write this as adding over all A prime, summation R, summation S prime, probability of R given S prime, times probability of A prime is, I'll just write S, times the probability of A given S. I mean, this is just I'm assuming you know conditional probability is better than, factorization is better than mean. And so see, what is this guy equal to? This guy is equal to this quantity here, which we will represent it as RSA. This is something that anybody who's learned any machine learning knows that that's the reward given the state and the action, right? And so this guy has just been reduced to summation A prime RSA times probability of A given S, game, set, match, championship. That's how you compute. Okay? Is that clear now? Oh, I'm here to answer your question. So, I'm a teacher, so I'm supposed to make sure that you all understand what I'm doing. Okay, we'll take it offline. Okay. So,
Don't worry, it won't be on the test.
sorry? Sorry?
No, I said, don't worry, it won't be on the test.
Okay, then in that case, I talk a lot, and I had a lot of ambition. Somebody was asking me what I was doing just before this meeting started. I was trying to derive this exact derivation here. Somebody asked me what the policy was and how do you compute the expectation. That's exactly what I was deriving. So anyway.
The microphone, please.
Okay, microphone. Okay. Okay, I'll show you all the data here. So the CD4 and CD8, all that good stuff we talked. I have 1.5 minutes, and I'll show you what happened. So negative here means that CD4 over CD8 is less than 1, and I'm looking at low WBC, and I'm estimating what is known as this Q function. I'm using Q learning within RL. It's looking at the Q value given a state and an action. So the higher values are good, lower values are bad. So negative, the CD4 over CD8 is less than 1. This person has a low WBC. Now what we got is that in the data that we have, like I said, somebody asked me this question. The preponderance of them get NRTI, and NRTI is always there. In addition to that, they'll get NNRTI or PI or both. So that's what you're looking at. In some cases, they get only NRTI. In other cases, they get NRTI plus NNRTI plus PI. That is the both case. In one case, you got only PI only and NNRTI only. In all cases, they have NRTI. And you see that, I want to make sure that I don't slip and fall. So you see that for a person who is negative, that means that it's a very high risk for HIV, and he has a low, and she has a low WBC. Both, we are seeing some signals. All this, the doctors are still not sure what we are seeing here. The point, like I said, I tried to protect myself at the very beginning by saying that we are applying RL to detect signals here between treatments, and we will be able to distinguish that. Medically, do they make sense? We do not know yet. We are still working on them. These doctors are difficult to find. And so, going back to your question that the gentleman asked at the very back, the first one was all about the top one was using only CD4 and CD8. The bottom, the middle one is using CD4 or CD8 plus WBC, and the last one is using HGB. So it's not just the metric CD4 over CD8, that ratio is called HS-RAT. It's not just HS-RAT that we are using, but we're also using WBC and HGB. I also wanted to talk about a number of things, such as the causality, how you can draw causal diagrams finding the relations between, how you take an antibody test, you take a test, an antigen test, and you look for antibodies. So the test is antecedent in antibodies. Antibodies will point to the viral load, and viral load is related to the outcome, which is the hemoglobin, it could be in this case, and then the intervention is the medication, which is the action. And that's in the book of Y, you would have seen the do calculus. The do part is just using that very intervention.
Has anyone here ever heard of do calculus or causal diagrams? Okay, there you go. Book of Y came out in 2018. If you hear someone say correlation is not causality, this is the answer to someone who's saying that. But thank you so much, Dr. CKL. Please give him a round of applause. So we did start a little late today, 30 minutes. So I'm just gonna go over about 30 seconds of slides, and then we'll keep mingling Higby so we can network and talk to each other. So if you haven't already, definitely check out the AITX community. They have a really great emails newsletter. It has a lot more of an Austin emphasis on new startups coming out, and the acquisitions, and the recent developments. It's a really great curated set of information. They also have events on the last Tuesdays to complement ours, which are the first Tuesdays. They're a broader audience. Again, we focus more on research. Jason here, one of the co-organizers of this group, brought this to my attention today. So there is a job opening. It's hybrid in San Francisco. It's called Attentive. So if you want to scan that QR code and take a look, it looks like they're...
Yeah, it's actually remote. Sorry, that's misinformation. Okay. Yeah, the first thing you can do when you're hired is fix the job description. You can totally stay on.
If they get an ML guy to do web dev, that's...
We both used to work as ML engineers, if anyone's curious.
Well, this is recorded, but at the bar you can tell everyone how. Yeah, so they have a good 200 to 300K salary range is what was listed on this. But yeah, take a shot of the QR code here if you want to take a further look. Does anyone else have any announcements? Eric, Jason, or anyone else? No? Okay. So yeah, we're also deep learning. We've been around for 8 years. We like to have various speakers on. Last month, for example, Joe here, or 2 months ago, Joe here spoke about how he's doing optimization It's an open source code base called Liminal. Before that, we had the DBRX model presented by Databricks. And then next month, we're going to have two of the regulars who come here give a talk on hardware. So we're going to have two 30-minute blocks. It's going to be the first time trying that out instead of the hour block. One's going to be from Grok, one's going to be from Maddox. They're both hardware companies accelerating AI inference, and they're regulars to this group. So yeah, it's Grok with a Q. So if you have anyone that you like, or if you want to give a talk on a paper that you wrote or that you even read, again, this isn't like a journal, it's something super formal, but we do like to get really in the nitty gritty and get our hands dirty on stuff. And if you want to give a talk, or if you know someone who does, just send me a message, come talk to me later. And again, I want to thank Capital Factory for hosting us here. So let's go on ahead and head our way over to Higbee's. But first, you have to clean up. We also got some free food from the last group, so I don't know who they are, but thanks to them, we're a little less hungry today. So just please clean up, put the chairs back where you got them. It looks pretty good already. And then just follow me and Eric. We're gonna go to Higbee's right after this. Thanks, guys.